All right, let me go ahead and get started. Good morning, everybody. Hope you're all doing well. I'm in Michigan, but I heard it's a little warmer in the Boston area. For those of you that are in the Boston area, I hope that is indeed true and rumor. We're really glad to be together again. Wanted to start with some housekeeping notes, which is to talk a little bit about where we are in the course and also talk a little bit about midterm logistics. I'll try to talk slowly for the first minute while those of you are arriving and getting logged in before I talk about midterm logistics. So where in the course? We have been doing supervised learning, and we are actually almost complete with supervised learning. We have 2 more lectures on that. I will be walking you all through max margin methods today, and then support vector machines on Tuesday. And then that will be it for supervised learning. The next lecture after that will be ethics, and then we'll begin to talk about unsupervised learning. One of the things that I want to mention is that you've been seeing quite a lot of mathematical material recently, and we do realize that. And you know, for good or for bad, you will be seeing more mathematical material today and on Tuesday. I know for some of you that's great, and for some of you that might be maybe not so great. So I just want you to know that the way I think about it is that the support vector machine material, which we're about to cover, is in some sense both the kind of like one of the technical highlights of the material in the course, but also one of the last places where you'll really be seeing maybe mathematically challenging material. That's not to say we won't be doing any math going forward, but I'm trying to say that if you've been following, you're going to see some more stuff that will look a bit tricky, but then the second half of the course actually changes flavor a little bit when we get into unsupervised methods. All right, and then I wanted to talk to midterm logistics, which we'll also be posting about online, but I know this will be on your mind, so we wanted to give you just kind of a sketch of how the midterm will go. First of all, the midterm will cover up to neural networks. It will not cover the material we're doing today or on Tuesday. So it will cover up to finale covered on Tuesday of this week. The midterms will be on Thursday the 11th, which is 2 weeks today. You will have 80 minutes for it. It will be a Zoom proctored midterm. We will be running the main session at 10:30 a.m. Eastern, but there will be 1 or 2 additional sessions for those of you who are unable to make the regular time of class, either because of class clicks or because of time zone. You will be writing your midterm unless you absolutely have to type, and you will be scanning and submitting your midterm at the end of the time period. The midterm itself will be downloaded by you from Canvas right before we get started. The midterm will be open notes, open book. We would encourage you to write one page maybe of notes down to help to organize your thinking about the material that we've seen. At the same time, the way we think about midterms is that it's not about memorization, and we will try hard to give you things that we wouldn't expect you to be able to memorize. Okay, so we don't want you to think about the midterm that way. And then a hard rule will be no searching, no typing, no communication. And when we say that the midterm will be Zoom proctored, you'll be in rooms on Zoom. There'll be a TF with you in that room, and you'll have your camera pointing at the writing that you're doing. That's how we want you to use your camera. And we realize that some of you may not be able to accommodate this, and there will be exceptions, but we expect all of you that can to accommodate that. Lastly, there will be review sessions the week of the midterm, and there will be a large, so the sections that week will be dedicated to review, and also there will be a review session. There will be example questions, and we'll try to provide specificity of the topics that we've covered that we think are very important for you to know and things that we consider kind of optional and extension topics. So I hope it helps, but please, if you have questions, now's a good time. I don't want to spend a lot of time this morning on this, but if you do have questions about midterm logistics, feel free to raise your hands or type into chat if anything I just said wasn't clear. Can you write on iPad? Yes, that seems fine. Al, and then Skylar.
Never mind, that was just my original question. If there's like pen and paper and iPad options.
Yeah, iPad is fine. Skylar?
Yeah, so I have the same question as Charu in the chat. Are there any practice midterms that we could reference?
We'll be giving practice questions out. So you will get practice questions.
Sure, thank you.
It will not be computational, if that's what you mean by mathematical, Raphael. It will be both, it will be conceptual and mathematical. You won't be writing code. You may be looking at some pseudo, like very high level algorithmic structure of code, but you won't be coding. And you won't be looking at detailed code. Other questions? Again, we'll be posting in detail about this on Ed, so we can also take the conversation there. But we were keen just to level set on this because we know there'll be some anxiety about the midterm with it coming up in 2 weeks. By the way, the second midterm is non-cumulative, if there's any confusion about that. Any other questions? Okay, great. So with that, we're going to start talking about this really nice idea, max margin methods. We're in our supervised learning world. We're talking about classification. We're non-probabilistic classification, so we're discrete. And max margin is an elegant theory that I'm going to walk you through this morning that takes us to the idea of a support vector machine model class. Neural networks are powerful, but neural networks have non-convex training problems. Max margin methods lead to convex training problems and lead to nice coherent theory. And while they may not have quite the absolutely wonderful accuracy of neural networks with very large data sets, they do have very good accuracy. But as I said, this leads to this idea of a support vector machine, effective for things like predicting a cancer type from cell samples or fake news characterization or predicting the function of proteins, and are especially nice when there are nonlinear interactions between features. And the reason that we'll see, we won't see that today, but the reason we will see on Tuesday is we'll see that because they handle basis functions very nicely. Here's just one example of the type of thing that support vector machine classifiers are able to do. This is using a support vector machine to try to classify whether a person in a video, and this is also reading off high confidence, moderate confidence, low confidence. And the way to think about this in the background is that there are features that are generated from the raw video image. Maybe think about tiling the video image where you're looking for information about the structure of the pixels in the image local to the tiles. But then you're doing this kind of higher level nonlinear interaction across individual tiles. And that's where basis functions will come in. And you kind of imagine trying to learn what are the interactions of the way pixels or more broadly the way tiles look like, such that you would tile a shape that would look like an individual. And you can find lots of examples of this type of thing online. In the background here, I want you to be thinking about what makes a good decision boundary. And here there are 4 choices, A, B, C, or D. And let's just maybe type into chat. So go ahead and chat out what you think is a good decision boundary here. Yeah, So D looks like a good decision boundary. We probably don't like A because it's not correctly separated. And then the question is, well, do we like B? Do we like C? Do we like D? Well, D certainly looks nice intuitively. And, you know, try to be thinking about why D might be nice. Maybe D is nice because if future data looks like noisy versions of current data, then if you use this boundary and your fit data is kind of a little bit higher, then it's going to start making mistakes. Kind of look for a boundary like this with a big gap to the examples can be useful intuitively. So this is what we're going to be talking about today. This is just an overview. I'm going to go through the math of all of this, but the idea is that we're looking for a decision boundary, a linear separator that maximizes the minimum distance from correctly classified examples to the boundary. So this point is at a minimum distance to the boundary. This point is at a minimum distance to the boundary. These points are all further away. And so you're finding a boundary that maximizes the distance to the closest point. And kind of this boundary is doing that well. And kind of the distance to the closest point is what we'd call the margin on the data. So this boundary gives you a good margin on the data. I'll go through this in some more detail. This is just to try to have you think about this in the right way. So here's another question. What's a good decision boundary? What do you think? A or B? Go ahead and chat what you think is a good answer here. Yeah, so not many takers of A's, a few takers of A's. Those of you that are saying A, you're saying A because you're saying, well, it's correct classifying my data. And those of you that are saying B are kind of trading a mistake here for a larger boundary on the data it's classifying correctly. And you know, it's hard to be definitive about this, but kind of the stance that we'll take is that this might be better. It might be nice to be able to pick out this type of decision boundary rather than this type of decision boundary. And this will be what we mean by a soft margin method that we'll get to in a few minutes. So here's a picture of that. Here are our blue points. Here are our red points. Here's our decision boundary that maximizes the margin while classifying all the points correctly. And if you say, well, I'm okay to make a mistake on this point, then you see how the data is actually the same data here as it is over here. You see how you can pick out a different decision boundary, and that decision boundary now has a larger margin on all the other points, and that might be better. And David's asking about minimizing max. That is what we're doing. Oh, I see. We're maximizing min. We're not minimizing max. Yeah. Yeah. Maybe think about that. Why that might be less interesting of an objective. I guess it's kind of that would pay attention to the points a long way away from the boundary. Last comment I want to make is that we're going to be talking about linear classifiers today, but we're going to get nonlinear on Tuesday. And this is the projection of a nonlinear decision boundary down to 2 dimensions. And everything will work very nicely. And that's where these techniques will become extremely powerful because they'll handle basis functions in a nice way. Yeah, so that's what we're up to today.
Yeah, these are, I just want to chime in and say these are super fun topics. David, you mentioned there's a lot of math, but it's very beautiful math for sure. And this idea of like images and features, like I remember in my graduate computer vision course was before neural nets took off. A lot of the very competitive algorithms were you ran convolutions over the image with some predetermined features or filters, and then you put an SVM on top. And there's a lot of industrial applications where you're trying to see parts on a conveyor, and you need to know whether the part is in the appropriate position or not. And at least at the time, these were all being done with filters with SVMs on top, because you want it to be robust to how shapes were aligned on those parts and these sorts of things. So these are immensely practical algorithms. And I had the opportunity to go see one of these like industrial vision-based sorting things at the recycling plant here in not outside of Cambridge. And it is just like, it's a ridiculously amazing thing to see, because the conveyor is moving so fast, and these plastics are being sorted by number, basically, just as they go through. And it's vision based, right? It's other parts of the recycling are sorted by metals or weight or stuff like this, but plastics are sorted based on optics.
That's amazing. Do you have a video to share with us?
I don't have a video. I mean, this was like,
come on,
we went to the plant, and this was before you were allowed to just like take your smartphone around. But it was, yeah. If you ever get the opportunity to go see the Casella plant here in the Boston area, take the opportunity.
Oh, that's so cool. Thanks for sharing that. All right, so let's jump in then to getting towards the method that we're talking about. So then, just as a recap, neural networks are good in the sense that they do what you might call representation learning. We talked about them kind of finding adaptively the right basis function to use. That's often called representation learning. They have excellent performance from an accuracy perspective, at least with enough data. But they are non-convex to train, kind of costly to train. And they are hard to interpret as well. There's a lot of work trying to interpret them, but they're still hard to interpret. You can try to point to the unit within the network and say, what's that unit capturing? But it's difficult. All right, and it's a bit of an art to kind of find the right architecture. So we're moving towards what are called support vector machines. Don't worry about where enough that phrasing comes from at the moment, but that's where we're heading towards. They allow for basis engineering. They won't automatically learn the right representations, but they give you a very nice way to think about how to engineer representations that you think will be powerful. They have very good performance. If we were teaching this class, let's say 5 to 8 years ago, we'd say this is the best method. Right? They were literally viewed as being validating. Now deep nets are viewed as being a little bit more exciting, but they are convex. They lead to convex training problems, which means that they are easy to train. They have simplicity. They're simple, interpretable. You won't see that so much today, but you will see on Tuesday when we talk about what a support vector is, and they have a coherent theory. So yes, I'm working hard for you to want to care about them because they are important, and I don't want you to think that you only need to care about neural networks. All right. What is our setting today? Our setting today is binary classification. And let me just maybe go with linear because we're just going to be doing linear today. So binary classification. And for now, assume separable data. We will relax this very soon, but for now, assume separable data. Picture to have in mind, just so we have it in our notes as well, is we can be thinking about data that looks like this, and we might have in mind either this decision boundary or this decision boundary. And this data is clearly separable, but I have more than one way to do it. And we're saying that I might prefer 1 to 2. The idea being is that it might be thought about as generalizing better. So you can kind of think about that as a small perturbation to the data will not matter. You'll still classify things correctly because the things are living away from the boundary. Any questions on that intuition? Okay. So what is, let me be a little bit more precise about this idea of a max margin. Let's go ahead and draw a decision boundary. I'm going to be annotating my decision boundaries with a plus when the weight vector will point in this direction as a positive discriminant and a minus. So a plus kind of means that the weight vector is pointing in this direction. And then we can go ahead and we can think about where our data might be with regard to the decision boundary. So there are example data points. And what is the margin? The margin on a correctly classified example is the distance. We have to be precise about what we mean by distance, but it's the distance between the correctly classified example and the decision boundary. So this is the margin. This is the margin on that example. This is the margin on the example. Okay. So that's the margin on an example. Let me write that down in words. So margin on a correctly classified example is the absolute normalized orthogonal distance to the boundary. There's a lot of jargon that I wrote down there, but we'll see that coming through in the math that I'm about to write down. And then the margin on the data is the min margin on correct examples. And we're looking to maximize the minimum margin. So goal. Remember, we're assuming the data can be separated at the moment. So the goal at the moment is to find a separator that maximizes margin. All right. So let's now do some geometry. We need to write down some math to try to capture what this margin quantity is. So for that, going to draw another picture. Here's my boundary. And let's imagine, and let's say this is plus, this is minus, and let's think about a positive point up here. And what we want to do is we want to think about the projection of that point onto the decision boundary, and then decomposing that example. So we're going to write X as its projection onto the boundary plus a vector that is orthogonal to the boundary. And so let's write out what that projection is. I mean, what the orthogonal is. We'll write that orthogonal vector, this vector here. We'll write that as a scalar r multiplied by the unit vector in the direction of the discriminant function of the classifier. Right, so this here is the unit vector that's going in the direction of W. Notice I'm dividing by the L2 norm to normalize it. That's why we use the word normalize up here. It's the orthogonal distance because it's in the direction of the discriminant vector, which is orthogonal to the boundary. Hopefully you remember that from earlier in the course. And so then R will be the size of that orthogonal vector. And now if we do a little bit of algebra, we can now write down a very simple expression for R. So let's left multiply by the transpose of the weight throughout. If I do that, I get W transpose X equal W transpose projection plus R W transpose W over the L2 norm. And for a point on the boundary, we can replace this expression with minus mu0, because this point is on the boundary, just using this equation. It becomes minus W0, and then we can rewrite the second piece as that because the numerator is just the square of the norm. And then from that, can rearrange terms, and we can conclude that R equal this quantity. So that's nice. So we have a nice simple expression now for the normalized orthogonal distance to the boundary of an example. And in particular, to make sure that we do that correctly for both positive examples and negative examples. So generally, for positive and negative examples, you just need to multiply by y. So generally, the expression I have is that the margin on an xn, yn example is yn multiplied by that expression that I derived. We're assuming here that this example is correctly classified, which means that for positive examples, it's exactly this expression. For negative examples, there's a negation that comes in because you would have a negative sign here. And we'd like this quantity to be positive, and so we multiply by -1 to make sure that it's positive. So just remember that this is always going to be positive for correctly classified examples by using y either +1 or -1. That's convenient. Any questions at this point? Okay. So let me make just a couple of notes here, just indicating the L2 norm is the 2 subscript. make a couple of notes. Note 1 is that the margin is invariant to multiplying W and W0 by some scalar with a negative. You can see that just by looking at the expression for the margin. If you multiply the numerator by beta, or if you multiply W and the W0 by beta, then you'll get a numerator that is that amount larger and the denominator that is also that amount larger. So the margin expression wouldn't change. Okay, so that's the first observation, that the margin, this orthogonal normalized absolute distance, doesn't depend on the scale with which you write down your W's. And if that seems mysterious, just remember that the decision boundary also doesn't depend on that scaling beta. You know, if you multiply the left-hand side by beta, it's still the same decision boundary. And I guess somebody's asking about my writing. What I mean to say here is that we want an expression that's general for positive and negative examples. Okay. All right, so that's my first observation. The margin is invariant multiplying by beta, but note that the discriminant value increases. Should have written a little in there. You multiply by beta, like the decision boundary doesn't change, but this point has a larger discriminant value. So that's the first thing that I want you to observe. That will be helpful in a second. And then the second thing I want you to observe is that if I just call this whole expression, call this whole thing star, star is negative if used on a misclassified example. To be clear, when we talk about margin, we generally mean to just define it on correctly classified examples. But if I did happen to take an incorrectly classified example and plug it into this math, this is going to give a negative value. That again will be useful in a second. Discriminant value is the H function. Discriminant value is this thing here. This is my discriminant. Okay. So then we can write down what is the hard max margin formulation. What is it? It's this. This is our training problem. Just plugged in the value that was calculated algebraically. That's all I did. What does this mean? Find the weights that maximize the minimum over all examples of the distance. Okay. This, because of point 2, this will find a separator if one exists, because this quantity will be negative if it's not a separator. So one thing to note is will find a separator. Remember, I'm assuming my data is separable at the moment. Because this quantity is negative if the point's incorrectly classified. So it can improve the minimum by pushing it to be correctly classified. So that's the first thing to observe. But then the second thing to observe is this looks ugly. I know that's a bit of a pejorative term to use about mathematics, but it looks ugly. It has this max min structure, and it has this 1 over L2 norm structure. And I don't know about you, but whenever I think about taking derivatives of things that are in the denominator, it just gets really complicated. So I'd rather not have to do that. Okay, because remember, we're thinking about using things like SGD to optimize these types of problems. So this looks ugly, but we do some neat things to simplify this. But I do just want to pause and make sure everybody's with me still. We're keeping W0 separate because notice that the rest of the weight parameters are playing a very special role. Remember how we got to this? We got to this by working with this orthogonal distance. And the W0 doesn't affect the direction of this vector. W0 just affects where this line is, not the direction. And so it's very important to recognize that W0 doesn't live here and doesn't live here. That's why we're keeping W0 separate. Any other questions? Okay. So, right, and we're multiplying by the reciprocal just because it's in the math that we derive to get the distance. You see how we've got this 1 over here? That's where that's coming from. Oh, I screwed this up. Apologies. I am sorry. This should not be here yet. Sorry. I'm so glad you asked. I had that twice. I definitely didn't want to have that twice. Thank you, Boris. Okay. So if that was confusing you all, then you were right to be confused. I just want to minimize the R. I don't want to have two 1 over L2 norm quants. Okay. So I'm going to pause again to make sure everybody's with me. And I'm glad that I did the first time. Are we good? Okay. Good. So now. How can we simplify this? So think about this as being maybe step 1. Let's do step 2. How can we simplify this? Remember that I talked about this invariance to beta. So by invariance to scaling by a beta greater than 0, without loss of generality, WLOG, to impose a new constraint on this problem. Remember I said that you can scale by beta, the margin doesn't change, because that's like in the numerator and the denominator of the margin expression. But of course, if we scale up by beta, then this quantity grows. What is this quantity? This quantity, I think if you ignore the y, which is just a 1 for a positively classified example, this quantity gets larger. So it's the discriminant value getting larger as I scale beta. And so if you're thinking about a setting where the data is being correctly classified, it's without loss of generality. Let me go back to this, this picture here, let's say. It's without loss of generality to require that the discriminant value on this example is weakly greater than 1, because I can arbitrarily scale up that W transpose X plus W0 function. And that doesn't affect the way we're calculating the margin, because the margin is the normalized distance. And so I can add this constraint to this formulation without changing the optimal margin. And I see that somebody's asking about max min, Lily, and you're asking about that. The way to read it, I think, is maybe helpful, is read it like that. So read it as finding the parameters W's that maximize the minimum value of this distance. And how do we deal with misclassified points? For now, I want you to realize that because our data is separable, there will be no misclassified points in the optimal solution here. And therefore, when I add this constraint, I'm not constraining the optimal solution. That's the crucial point. So let me go ahead and add that constraint. Now I'm going to pull that reciprocal to norm outside of the min, because it's the same for every example. Oops. Okay. And then I'm going to add new constraints subject to for all n. I can add that constraint without changing my optimal solution. It's a choice that I can make. Let me draw a little picture in a second to help you to think about that. Before I draw the little picture, I want to now point out that this is equivalent to an even simpler formulation. Because we are trying to find W's that maximize this minimum quantity, one or more of these constraints will be binding. Think about it this way. So this is because one or more constraints will bind. Bind means they will be tight. They will be equal to one, not strictly larger than one. Think about it this way. Suppose that I claim to you that I have solved this problem, and yet yet all of my constraints are holding strictly. They're all strictly greater than one. Then you could say no, that like there's no way you've solved the problem, because you could choose a smaller weight vector, just scale it down by a positive quantity. You would still be satisfying this constraint. But if you reduce your weight vector, then you've increased the reciprocal of the norm. So you weren't optimizing. There is a smaller weight vector, therefore a larger reciprocal of L2 norm that would still satisfy the constraint. Therefore, one or two constraints, one or more constraints will bind. And notice that that dramatically simplifies this expression, because that means that the minimum over all examples in an optimal solution will be exactly one. So the objective just becomes max of the reciprocal of the L2 norm subject to this point. So therefore, I claim that this is an equivalent formulation. It's equivalent because one or more of the constraints will be binding. And this leads to what we will call our hard margin formulation of the max margin training problem. Notice that I got rid of the max min, and now I'm going to get rid of the reciprocal. I'm going to recognize that maximizing the reciprocal of the L2 norm I could equivalently be minimizing the norm, or equivalently, I could be minimizing the square of 2 norm, because that's a monotone transform. So I can instead write this as min WW0 of the squared L2 norm subject to this constraint. And this is nice. And I'll draw a picture in a second. This is nice because this is convex. Notice it has a quadratic objective. So it kind of looks like this, and linear constraints. So we have a convex training problem, like I promised you. And also notice that because one of these constraints will be binding, the margin will be equal to 1 over the L2. So once you've solved your problem, you take your weight vector and 1 over the L2 norm will give you the margin on your data at your solution. And I want to draw a picture now, which I hope will help this all to make sense. So here's my disk boundary. Plus minus weight vector going in this direction. And here is the positive margin boundary. Here is the negative margin boundary. So call that a margin boundary. And remember that we've added this constraint that says that that discriminant value described by the left-hand side here has to be larger than 1 for positive examples and smaller than -1 for negative examples. So that means that the way to think about this is there will be some examples that are living right on that margin boundary, and there'll be other examples that are living away from the margin boundaries. And because the data is separable, all of the data will be correctly classified, and none of the data will be living within the margin boundary because of the constraint that we've added, which was without loss of generality because of the scaling argument. Any questions about this? This will be a good point also to take a short break. So those of you that want to walk around, grab a cup of tea, good moment to do that. And I'll take questions for a couple of minutes. Haritosh, you're asking, why do we have the minimum? Oh, did I write something wrong? No, this is good, right? So I started with the max of the reciprocal, and now I've got the minimum of the non-reciprocal, and I've also squared, and I can square because square is a monotone transform. So I don't change the objective by squaring. Was that your question, or is there some other problem with my notation? Okay, great. I'm looking at Viet's question. Viet asks, when we scale W down in the case where every constraint holds strictly, the minimum inside will drop a little while the coefficient increases. How do we resolve this predicament of reason the min should be 1? We're adding a constraint. So we're not going to allow the discriminant value to be less than 1. We've added constraints. Okay. We've added this constraint. So we don't have to worry about that trade-off. It can't go below 1. And yeah, Cherry's asking about squaring. Exactly, it's going to make things easier. Any other questions? Particularly by squaring, we get the quadratic in the denominator, in the objective that we like. Okay, so you have just seen part one of a three-part beautiful mathematical theory. You will see the second part today. You will not see the third part today. You will see the third part on Tuesday. We've just done hard margin training. And now I want to talk about soft margin training. So soft margin formulation. And this is motivated by a desire for regularization and by a desire to handle non-separable data. So as a reminder, you think about your data like this. You might actually prefer two over one, even though two is not separating the data. And the intuition is that two may perform better on unseen data. You think about that unseen data as being points that are perturbed around the data that I have. And also the data may just not be linearly separable. Just a comment on that. This formulation we just arrived, this thing explodes. It doesn't work if the data is not separable because of this hard constraint. This hard constraint requires that the data be separable. So the solver would just say, ah, sorry, unfeasible, which is not very satisfactory for your training process. So we need to do something a little bit different. What we're going to do is we are going to use a relaxed formulation of that problem. Is my decision boundary. Here's my positive margin boundary. And here's my negative margin boundary. And we're going to introduce a new variable, C. I'm sorry, you have to somehow figure out how to write X's. That was actually not a very good attempt. I'm used to doing \xi. Let me try again. I knew this was going to be the hardest part of today's lecture. So that's a C in LaTeX, \xi. Introduce a new variable for each data point, which is non-negative. So this is for each example, little m. And what it will mean is how much is xn on the wrong side of the margin boundary, not decision boundary, margin boundary. So let's start drawing some examples of this. Here's a point that's on the correct side of the margin boundary. So Cn is 0. Here's a point that's right on the boundary. Cn equals 0. Here's a point that is living inside the margin. Cn is greater than 0. Notice it's less than 1 because it's not yet over the decision boundary. And here's a point that is on the wrong side of the decision boundary. So it has a Cn that's strictly larger than 1. It's less than 2, actually, because it's yet crossed this part of the boundary, but it's larger than 1. And so what will we say? We'll say that if Cn is 0, then it's correct, classified, and there's no problem with the margin either. If 0 is between, if Cn is between 0 and 1, then that point is correctly classified, but has a smaller margin than 1 over the L2 norm. Remember that all of these points on this margin boundary here have margin 1 over the L2 norm of W. These points, because their discriminant is 1, and that goes in the numerator, and then we divide by the L2 norm to get the R value that I described earlier. These points up here have margin greater than 1 over the L2 norm of W. And these points here are correctly classified, but have margin smaller than 1 over the L2 norm. And these points here are incorrectly classified. So if Cn is, then they're incorrect classified. Cn is greater than 1. Okay, does that all make sense? Any questions? Because what we're going to do now is we're going to use this new variable, a new formulation. And this is our soft margin formulation. So now, for some C greater than 0, and this will be a regularization parameter. We're going to write down this new formulation. And rather than the square of the L2 norm, I'm just going to write it as the inner product. And then here's the new bit. So we're adding this new part of our objective. This hasn't changed. This part's as it was before. This part is new. It's C multiplied by the sum of the Cn's, capital C, multiplied by the sum of the Greeks. Subject to, here's the same constraint that we had before, except we're going to slightly modify it. This is where we get our relaxation. Here's our new formulation. So let's look at this and understand what happened. So I used to have, this constraint used to be weakly greater than 1. And now I'm allowing it to be weakly greater than some quantity smaller than 1. For example, if the left-hand side was 0.5, that's okay, but notice that Cn would need 0.5 to compensate. If the left-hand side was 0.2, so we're getting closer and closer to the decision boundary, then Cn would need to be 0.8 to make that okay. So that I've brought in the Cn to the right-hand side, which is non-negative, is a relaxation. It's letting me not quite satisfy this inequality. if I choose not to as an optimizer. But I penalize myself whenever I do that in the objective. So it's not free. You face a penalty of C multiplied by the sum of the relaxations. And let me kind of help you interpret this. One is that we can kind of pretend that the margin is 1 over the L2 norm. It's strictly only that for the points that are on the correct side of the decision margin. Right? So we're kind of ignoring examples that live in the margin. If you go back to my picture, there are going to be some points like this point here. This point doesn't have a margin of 1 over W. These points do up here, but this point here doesn't. So we're kind of, well, it's like we're kind of pretending that the margin is still 1 over W, even though it's not on all of the examples. That's one thing to notice. Second thing to notice is that this allows for misclassified points. So I've been kind of talking about the discriminant being less than 1, but the discriminant on a positive example could go negative. That's allowed. It could be -1. Then the CN would be 2 to compensate. But we no longer strictly insist on a separator. So it allows for misclassified, sorry, is my writing not good? Misclassified points. Thirdly, a large C, and in particular, C equal infinity is hard margin, is less regularization. Why? Well, because it's trying to get the correct classification on all N. I think mistakes matter more. Don't make mistakes. So smaller C, less, larger C, less regularization. Don't get that confused. Larger C, less regularization. Kind of the converse, smaller C is going to give you better 1 over L2 norm, which kind of the margin, like we're pretending it's the margin because we're ignoring those points that are lurking in the margin boundary, and will allow for more mistakes. Any quick questions? I want to do one more thing. Better in the sense that it will be larger. I want to do one more thing and then we'll move to concept check. I want to first of all just note, I guess 2 more things. First, I want to note that I can write this formulation in a slightly simpler way by solving for the CN analytically. And the CN is always going to be either 0 or 1 minus the left-hand side. I think you probably saw that when I was giving you examples earlier. So equivalently, we can write this. I don't need my CNs anymore. So now it's just max of 0 and the right-hand side minus the left-hand side. So equivalent formulation, hopefully you can see that if you're trying to minimize the subjective, you should never have your CN be anything other than the max of 0 and 1 minus that discriminant quantity. And the reason I'm telling you this is that this is convex. You can see now why this is convex, because this part is kind of shaped like a quadratic, and this part is shaped like this, because it's a max of 0 and a linear quantity. It looks like that hinge function that we saw earlier in the semester. And the sum of the positive sum of functions is convex. And it's also differentiable almost everywhere. Differentiable almost everywhere. So we can use SGD and be confident that things will work. And then I want to make a couple of notes, and then we'll go to concept check. Note 1, I want to compare loss functions. This is what I really enjoy about this material, is pairing the different loss functions. So remember this picture that I drew for you here? This is my discriminant value, and this is, let's say, for a negative example. So positive means that we're misclassifying. And here was my 0, 1 function, my 0, 1 loss function, which was not differentiable. Here was my hinge loss, which was differentiable almost everywhere except right at the origin. Here is my logistic loss, which remember we liked because it wants to push points away from the boundary. We like that it has this tail over here, whereas the hinge loss function does not. We like this. It says, make it move away from the boundary. And now we see very clearly what our softmax formulated SVM tells us is our loss function, because it has this max of 0, 1 minus discriminant value to it. And if you think about what that means, it means if the discriminant is 0, then the implied loss is 1, because you're 1 away from the margin boundary where you want to live. If the discriminant, this is for a negative example, if the discriminant is -1, then life is good. You're on the margin boundary, you're happy. And this is linear above here. So my support vector, my soft margin support vector formulation looks like this. That's cool. We got that through the derivation we've just all done together. And you might be wondering now, well, why is it better than logistic? You probably see why it's better than hinge, because hinge doesn't have that tail to the left that I like. But why is it better than logistic? And the answer we don't see yet, but we'll see next class. The answer is that because it's got this kind of quadratic and linear constraint form, we can do some duality math next class and get nice basis functions. Works with base functions nicely. So it turns out that it's just like a slightly simpler mathematical form, and that's really helpful. Last note I'll make is that, reminder again, why are we talking about large margins? Large margins help to generalize. Think about small perturbations. Okay. So what we'll do now is we'll do a concept check. And maybe, Finale, if you wouldn't mind setting up the breakout rooms, that would be awesome. Here's the concept check that you're going to do. And I'll also chat it. First of all, suppose this was your data with the max margin boundary shown. First question, removing which of the blue plus and negative points will change the max margin boundary? You can check any number of options. Next question, here's the soft margin training problem. Thinking about changes to C, this capital C here, which of the following is true? You can check any number of options. For very large C, the optimal decision boundary will try to separate the data if possible. As C increases, the formulation allows higher error in classification on the examples. As C increases, the formulation is more able to bend with the data. Question 3, what is the effect of higher C on the regularization? High regularization, lower regularization, can't say. Ignition 4, that shouldn't be there. Okay, so we're going to send you into your breakout rooms, and we'll bring you back in 3 minutes, and I'll quickly wrap up.
And David, I forgot to mention before, but I will have to leave around 11:50. We have a guest coming at noon.
No problem.
So it shouldn't be a big deal.
No problemo. Just trying to get to the answers. Let's see. How do you see the answers coming in? Let's see.
Is there on the top
Oh,
of the Google form,
okay.
is there responses?
Yeah, I see them now. Okay, we can bring them back in. I see. I can close. I'll close them. All right. So welcome back. Just to wrap this up. question 1, there was lots of support for removing this point affecting the boundary, and there was moderate support for removing the negative points affecting the boundary. The answer is that removing any of these 3 points would affect the boundary. I just kind of would encourage you to think about it offline. I guess you probably also visually that if you remove this positive point, you have an opportunity to move the boundary so that it's further away from these points. And then maybe just to think about, let's say, this negative point here, probably you can see that if you remove that point, you have an opportunity to be further away from this point. Thinking about drawing a line connecting these two and splitting the difference and drawing an orthogonal to that line, that would be the new decision boundary if you didn't have negative points. And the same thing with removing this negative point, although it's not quite as clear how you can do slightly better. But again, you'd want to orient your line this way. Okay, so hopefully, at least I think that would be better. Yeah, because it would still be further away from this point. So that's the first question. And then in regards to this question, I think most of you got this right. Yes, for very large C, the optimal decision boundary will try very hard to separate the data. No, as C increases, it does not allow higher error in classification, it allows lower error in classification on the data. As C increases, the formulation is more able to bend with the data. Yeah, maybe that slightly misphrased, like the more able to, but it will choose to better fit the data. And when we generally think about non-linear functions, which we will soon, it really will try to work hard to conform to the data or to bend with the data. And then question 3, what is the effect of higher C on the regularization? As I emphasized, higher regularization. You wouldn't be able to say whether higher C would improve generalization performance, but you should be able to say that it's more, lower regularization, which is what you all said. I just made the slip. Higher C, lower regularization, which is what you all said, pretty much all of you. You wouldn't be able to say, if you're saying can't say because you weren't sure if I was talking about the generalization error, that's right. You don't actually know whether the generalization error will be better or worse. But just from how we think about regularization, it will pay less attention to the data. It will have lower variance, higher bias, will be less well regularized. Great. So I'm gonna hang around. Sorry, we went a couple of minutes over. And we'll stop the recording. Feel free to ask any questions.